Welcome to now the fourth episode of How Does a Computer Work? A bottom-up explanation. Today we will be talking about logic. Um, Quickly here, one at a time again, a little graph where we are currently. Probably logic is going to be 2 episodes, so there will be another one coming out soon about logic. And yeah, we're just gonna go into logic, kind of define what is even logic. We have so-called logic statements that are basically statements that are either true or false, basically. So I've written down a few statements and we're gonna discuss them a little bit. First one is you are watching this video, your computer is on. Basically, yeah, if you're watching this video, you most likely are watching this on a computer. I will just call your phone a computer as well in this case because it technically is. We discussed this in the first episode. So this would be a statement that is true. You cannot watch this video without having a computer turned on. Then, second one, veggie burgers are made out of meat. That is also a statement in this case, but the value of the statement is false because veggie burgers by definition are not made out of meat because they're vegetarian and vegetarian things cannot contain meat. Simple thing. So statements can be either true or false. Whoops, I accidentally put a little point. Can draw on things now here. So yeah. So either true or false, that's what can happen with logic statements, or like the states they can be. Then I have two more things that are not statements. First of all, we have this sentence is wrong. This is a paradoxon, meaning it is neither true or false, so it is not a statement. And also, welcome to this video. Hello. Yeah, this has no truth or a false value. Basically, you cannot assign it as true or false, so it is not a statement, and I am in front of the thing again. It's not a statement, neither true nor false. That's what it says behind me. I should have thought more about the things, where I put them, but yeah, we just continue. Then there's a few properties of statements where we can assign. First of all, in the first statement up ahead, you have the statement Peter is lap, every lap is drell, thus Peter is drell. And I'm just first think about it, is it true or false? What is written there? And yeah, I think most of you will have thought this is true, a true statement. Well, it in fact is, even though we don't even know what lap is, and we also don't know what drell is. So yeah, we do not need to know what exactly we are talking about. We don't need the details. We can establish true or false without knowing what lap is, what drell is. Doesn't matter for us. And we can also say A is correct or B is correct. This is also a statement. We can substitute those things for variables or other inserts, basically, because yeah, we don't need to know what it is in the first place, so we don't need to give it a specific name. It doesn't need to be named. Yeah, and the last one, only one of A and B are correct, and are A or B and not A and B are correct. Those statements are equal. You can go through that. Basically, we can rephrase statements. There are a whole set of rules for that. And you can just Google logic equation rules or logic transformation, and there should be a Wikipedia page where you can look up the rules about it. We're gonna do a little bit about it in the next video, which is going to be about reforming those statements and like making statements in a way. Yeah, but that's a few properties we have, and we can now go into logic calculation, or like the basics for that. We're not gonna do any calculation yet, just showing how the syntax is basically. First of all, we have truth tables. In logic, you're gonna be often seeing truth tables. For now, I put the truth table to the value of A or B. So basically, we get as our solution, or like the first two are which value has what value A has is down here, what value B has is down here, basically, and the solution is here, and it's basically in the sense that. And yeah, a little note on that: in logic, in the mathematical form of logic, or always means and or, basically, our language and or. For the not and or, like or without and, there's a different type of or. Here we have always like either one or both are can be correct, so that's logic or. Always keep that in mind. But that's how truth tables are built. They can be a bit longer, they can have more variables, and often you don't know that this here is for or, basically, and you have to kind of establish that yourself, find that out yourself. Next one, common logic operations and syntax, of course. First of all, for our values we have here, the first thing, our first list, true, is basically if a value is true. Often we write that as a 1, or here's also alternate form. We can sometimes in mathematics you write T, and sometimes in informatics you also write H for high. High is like a signal if you have like a high like positive voltage going through, or like pull up, pull down, it's called like that. And yeah, if you have the high signal going through. And yeah, the other one is false. In this one I'm going to be using the 0, and other ones are false, like F for false and L for low. And then there's a third thing, which is either neither or don't care. Neither is mostly not going to be used in especially computers, because that doesn't really exist technically. We don't have a neither because you would need a third type of signal for that. But sometimes we have don't care signals, which means they can be 1 or they can be 0, it doesn't matter. And later in logic calculation we can take that as a little bonus, because we can assign them either one, and that property makes us able to shorten some things down way easier, because we can discard a few statements basically later on, but this is going to be in the next video, not here. And standard operations are or, which I've shown below, above, like in the last slide already. A plus B is usually how I'm going to write it. Alternate form, that's also the form you will see on Wikipedia, is A, and like this, just arrow down, B. And then there is and, so A and B, which is in the alternate form arrow up, basically. That's written on Wikipedia like this. And then there's not, I don't know why on the slideshow, but the line is like supposed to go over the thing, like this, like A with a line over it is not. And yeah, and sometimes you have like this like weird sign here, which stands for not, like this minus with like a little thing going down, which is also not, basically. And then there is A XOR B. XOR is our explicit OR, so that's either one or the other, not both. That's the form. I'm just gonna show you this one here, but often in computer science, XOR gets like just completely deleted out of the things. We usually don't use XOR because A, B equals, we have A or B, and not and, yes, and I just write it a bit smaller. We have A or B and not A and B. That is the same as XOR, and if we have a one operand less, it is a bit easier. We don't need to remember that many rules, basically, and that many operands. Yeah, so and all kinds of logic statements. There's also logic statements like this one: A, uh, A follows B. No, B follows A. Like if B true, then A is no A. This one is basically if A is true, then B is also true. That means, and others can be all shortened down to just three operands: or, and not. That's the ones we need. With that, we can make any kind of logic statements. We can reform all logic statements that use other operands into that one, and it works. And yeah, most often in computer science, you just do that, so you have less things to worry about. You have to make less gates because it's just a bit easier. Yeah, that's common logic operations. And we go to the next one. Here's like a truth table of our logic operations again. So we have our values here, our A and B we have here, and in every column we have written what the solution would be for the specific type of operation. So A or B in this sense. If A and B are both false, A or B is also false. As soon as one of A and B is true, A or B is true, and A and B is always false, except when both A and B are true. Not A is only true if A is false, and not A and B. Just shown that you can write it this way. If you can basically put the line above like sections and negate the whole section. So this is basically A, not A and B in a sense are just the opposite of A and B. So it's basically A and B, but every true turns into a false. Just negates the whole thing. And yeah, just here written again, A, X, or B. That's just how that works. If one of A and B is true, but not both together. And that's just a little bit of an explanation for logic operations. And of course, we want to have the whole thing as circuits also, because we're gonna make circuits out of that, basically, to actually transform that into transistors later on. Because yeah, we don't have we cannot just write a whole mathematic equation like Q equals A plus B and not B something. That is a bit, yeah, we can't just write that on a circuit board and call it a day. Now we have to make logic circuits, and these are all most of the signs. Just gonna show you first. We have not A in the sense. Basically, this triangle just is like an empty type of thing, and the circle in front here shows that it's not. It's negating a thing. This thing is here says, yeah, basically just and. For or we have like the same thing, but it's like spiky. Yeah, it's like looking like arrowhead, and XOR, there's also a little thing for that, which is just OR with like this added line. And the last one, just to show you, we can negate anything by putting this little circle. So if we put this little circle here, basically, it makes the whole thing into not A or B. So instead of A or B, it's not A or B. And we can, of course, also negate inputs. So we can also just say, okay, we want not A and B. So in the sense, if we put that, we would just negate our A before. So the input of A gets flipped, technically. So if A is true, it goes into the AND as false, kinda. You have to imagine that. That's what the little circle does, and you can just like if you can like negate single lines. Just say, okay, I don't want this one. Like I want this one false, this one true. Then like you want not A and B. Then you do this basically, and that's how those gates work. That's like the standard American or like the international way of writing it down. There is country-wise sometimes different ways. I know Germany has a different way of writing the whole thing. So that's just there. The gates look a little bit different. Do I remember them? There it would be, for example, I just remember the thing. It looks a bit like this, and you have, I think, +1 technically, so it's 1 or 2 signals in there. Would be the OR, but yeah, I'm just gonna do the international one because it's just easier when you stay with one. You can look up the other standards as well, though, if you like. And of course, we can reform logic formulas as written below here into the logic gates thing, like written. Because yeah, this one would be transferred to exactly this here. So we basically go from what we calculate first. So in the brackets we have A and B that we do here, and then we have A XOR B that we have here, and then we connect that all together. Like the outputs of those two will be put will be ORed. You can't say that well in English. The outputs of A and B and A XOR B will be calculated with an OR. So you put the OR as last one and take the outputs of either of both of the things and put them in here. Of course, in a computer the whole thing is gonna be a bit more complicated than that, but just as a little basics for now, you can do that, and we will be going into especially the transformations and the rules of this a bit more. Also, yeah, you can look up in Wikipedia the rules. They're also written there. And for today, that's already it. I just used, there was a few more pictures, but they're all from the Wikipedia org logic gate. So if you want to look them up, it's also a bit written about it there, of course, but yeah, Wikipedia can be quite complex sometimes. but that's where the pictures are from, and they're open source. Or not really open source. They're in the I forgot it, but not open source. But everybody can use it because they're like there is no I can you can just use the picture without any rights for it, and you don't even have to give credit and stuff like that. Still, link for the pic to the pictures is in the description, and the video's over now. I got a bit sidetracked here quickly, but yeah, I wish you a goodbye. Have a nice day. Um, yeah, I'm still again here, huh? Yeah, okay, this time I'm not gonna do any like longer explaining you why you can go away. I'm just gonna go away now. Goodbye. I'm just gonna go away. Seriously.